I'm the taxi. How much should I? OK, so I'm going to talk about something funky that we call signatures of work. And more like or, how to bypass, circumvent a consensus impossibility result. OK? And that comes from the blockchain area. And I like to second Alon, who's not here, to say that one should be open to new ideas, regardless of how nonsensical they are, new views, new insights about doing things. So by the end of the presentation, I should be able to explain this beautiful picture, okay, which is what we call a consensus taxonomy that we sketched up with Angelos Kiayas sometime last year, and we keep modifying it. There is some apparent inconsistency here that we're going to try to explain in this talk. All right, so the thing is about consensus broadcast, which is one of the most fundamental problems in distributed computing, fault-tolerant distributed computing, important role in cryptographic protocols, secure multi-party computation. And it has received renewed interest with the advent of blockchain protocols like Bitcoin, suggesting new ways of doing things, wider research community, other applications, and so forth. All right, so that's the theme. So I'll tell you what this consensus business is about that you might already know. So we have n parties, T corrupted, all start with an initial value. There's an adversary corrupting some of them. They run this consensus protocol, and they have to output a value that has to be the same. Okay, specifically, without loss generality, we can focus on binary input values. And essentially, it has this is captured by these properties. Agreement, meaning everybody has to agree. The same value, they have to output the same value. Validity means that if all honest guys start with the same value, there has to be the outcome, and it has to terminate. Okay, that's the consensus problem. Everybody has an input. And important also in crypto is the single sender. I think by the end of the week, I'm going to get used to this uphill thing. Yeah. So, and the single sender version of the problem called broadcast is, that we use in cryptographic protocols. When you broadcast stuff to all other parties. And then the validity condition is, if the sender is honest, then there has to be the outcome, the output. And here's the broadcast version, okay, with the properties conditions repeated. And as I mentioned, fundamental problem in distributed computing and cryptographic protocols. All right. So this traditional setting, what were the traditional complexity measures? First was the running time, measure the number of rounds. It has, in the deterministic case, has to be t plus 1. You're not going to pay too much attention to that. In terms of how many corruptions the protocol can tolerate, call that resiliency. In the unconditional setting, this problem formulated by Lamport et al., they show that it has to be bigger than, n has to be bigger than 3t. Okay? And so here's why. Here we're looking at the broadcast problem, version of the problem. So we have a sender, two receivers. Blue means corrupted. So here the guy says send the same value to both, attack, right? And here they relay. They have to exchange values, relaying what the guy is sent them. Okay, and here in this scenario, so as not to violate validity, this guy, the other honest guy, has to do what the sender suggested, right? In this scenario, the sender is corrupted, okay, and he says conflicting values to these two guys. These guys are honest, so they just relay honestly the values. And then they have the same scenario, distinguishable, one from the other. Okay, so this guy has to do the same thing, has to attack, and symmetrically he has to retreat. So that violates agreement. Okay, that was a basic informal sketch of the impossibility result for n less equal 3t. All right? And that was in the unconditional setting. In the cryptographic setting, also we have n parties. T of them might be corrupted. The subset of parties has to be might be corrupted. So in the cryptographic setting, things are somewhat different. So here, this bound holds for both the broadcast and the consensus version. In the cryptographic setting, broadcasts can be achieved with arbitrary number of corruptions. Okay, this was shown by Dolev and Strong in the early 80s, and this is a protocol still used when you want to do a broadcast in the cryptographic setting, at least feasibility-wise. But consensus is you need a majority. Yes, that's one of the inconsistencies that we are trying to resolve in this talk. The running times for deterministic. This is for anything. Okay, never mind message complexity. And as Yuval pointed out, so this is what you achieve in the cryptographic setting. And this is what Dolev and Strong assume. So there is a public key infrastructure, okay, and secure signatures. Okay, so in that setting, they show this stuff. You can achieve this optimal number of rounds, deterministic, never mind, and polynomial time complexity. So it was much easier in the cryptographic setting than in the unconditional setting to achieve this. Was achieved early on. Okay, and this is just to give an idea, because we're going to contrast this to the approach in the blockchain, from the blockchain approach. But it's pretty much, this is the simple protocol that Dolev Strong suggested. So we use the broadcast version. The source signs a value and sends to everybody, right? And then the parties then do this for t+1 rounds. Okay, so they keep track. So they store a message signed by the sender, right? And they relay. If at any point they receive another message sent by the sender, they also store it and they relay. Okay, and at the end, then if they have a contradiction, the same different message sent by the sender, they output the default value. Otherwise, they output this value, which should be unanimous. Okay, so very simple protocol. All right, okay. And that's what I said. Only one except if this said there's only one value signed by the sender, that's the output value. Otherwise, some other default value. And that was cryptographic. So in the important work was the introduction of randomization to distributed algorithms by Benor Rabin, okay, who showed actually this problem can be reduced to a common coin, okay, the random common coin, which was in this major result by Feldman-Bicali. Now you have your local randomness. You want to establish a common random coin right from scratch. No trusted setup and so forth. That was Feldman-Bicali, 88. And then in the cryptographic setting, this was information theoretic, cryptographic setting later on by Katz-Ku. All right, so that was a brief introduction to consensus and classical results. And Yuval insisted several times that there should be lower bounds in everywhere. So these are lesser known lower bounds, okay? And interestingly, when distributed computing community talks about cryptographic, consensus broadcast in cryptographic setting, they assume that you can run this Dolev-Strong thing and that you can reach consensus for arbitrary number of corruptions. Okay, which is not the case. So there's a lesser known impossibility result that says you cannot relate up to a minority of corruptions. Okay, and this was some sort of was floating around until Fitzy was one of the first ones to formulate this scenario. And he says, well, just split you have n parties, split them into two halves, half as 0, half as 1, and now the adversary corrupts nobody, probability a third, the guys with P0 that have 0 probability a third, and P1 probability a third. Okay? And after that, it runs, follows the protocol. Okay, it turns out that here they have to converge to agreement. In this case, 2 and 3, they have to convert to 1 and 0. Okay, depending on who's the guys who were not corrupted were, and these situations are indistinguishable. Okay, so easily formulated, and that gives us that result. Second, perhaps less known impossibility result is also what Yuval mentioned. So what happens when you don't have a PKI? Okay.
So is there some, because validity is really just there to avoid some non-triviality of the protocol. And so is there some way to reformulate validity in another way that bypasses this? Yeah, it's a very big question.
Yeah.
It seems very tailored at this time.
Yeah, so there are weaker versions of, but I have, let me, so this is lesser known, and this is from Borderding in 96 that show, well, you don't have a PKI, so intuitively that makes sense, right? You don't have PKI, so you sign something doesn't mean anything, right? And as you can see, look at the similarities between what we had before and this picture. And here essentially saying, so these guys could, the sender could distribute arbitrary keys, for party B, party C. The guy then sign. In this case, for example, this guy is corrupted, right? So he sends conflicting messages. And here the sender is corrupted, so he sends signed, see this A, B, never mind the notation, but this is saying, with the key that I gave to party B, the key that I gave to party C, and so forth. So the crypto doesn't help. Okay, so he can play the same scenario without a PKI. Borderding from Karlsruhe. And now I got Dennis' attention. Okay, so I think it was a master's thesis, and
wasn't the original LP server, wasn't the attack player, the attacker was just doing the honest purpose protocol. Even there's different situations, but you don't need, even with computational assumptions, the attack would go through.
So in this part of the literature, all this was implicit, right? So it was signatures is because there's a PKI, so you have signatures, you cannot do this. So you have to come, from other angle to start looking at these assumptions. And okay, so all right. So we said new stuff coming from the blockchain space, blockchain-based consensus, and now I have to tell you briefly, some base, blockchain basic stuff, and I'll go quick. Okay, so part is miners trying to build a blockchain, chains of blocks look like this. Okay, and in each block, what you have is, at high level, hash of the previous block, some data, and a proof of work. So data could be a transaction. This is a Bitcoin-looking transaction. But in the application we're going to see, here we're going to have like input values. Okay, looking ahead, the miners are going to be the guys trying to agree on something. So they're going to try to, so the transaction field is going to contain the party's input values. Okay, proof of work, cryptographic puzzle, important, cool stuff by Dorg Naor and many other follow-ups to combat spam mitigation, Sybil attacks. Here's Sybil. Okay, this is a real book called Sybil. A psychiatrist wrote about a patient that had multiple personality disorders. And arguably the most impactful application is this stuff, blockchain protocols, where things are organized like this, right? You have some state, you have some new transactions, you hash all this stuff, which is here. You have some witness, right? You hash this stuff again, it has to be less than some target value. Okay, you keep going, and there are rules to why this works. And okay, and they all notice that they all start from this initial block called Genesis block. Okay, here's transaction, and the point I'm making here is that if you want to do like double spending or have the chain, fork and go some other way, because there is a transaction here that you want to avoid, you want the whole system to go this way, but to do this, if the transaction is sufficiently deep, the thing should be immutable, and unless you have the adversary controls the majority of the computational power. Okay, so basic intro. So what we did with Chiayas and Leonardo's was we came up with the abstraction of this blockchain Bitcoin protocol that we call the Bitcoin backbone. Okay, we analyzed this under a cryptographic adversary, meaning the corrupted guy can do whatever they want. We analyzed the core, and in some sense, we separated the data structure part, the blockchain part, from the application stuff. Right? Transactions have to agree, have to be the same, Bitcoin, and so forth. And we do this by specifying functions, predicates, such that you can, in principle, specify any arbitrary application that runs on this stuff just by instantiating this function. Okay, the V for the content validation thing should be all the transactions that are in these data structures to be consistent according to some definition. Okay, in Bitcoin, the guy who moves funds has to be enough, the balance has to be big enough to be able to, make that transaction type thing. All right, so for this, we came up with a model, somewhat idealized model that I'll mention because we're going to come back to this later. This is all standard crypto stuff. For the communication, we have this primitive called diffusion, which is like a TCP/IP-like primitive, right? Based on peer-to-peer connectivity, they just put stuff in the network and then it diffuses, right? So it's reliable, okay, but it's not authenticated. It means adversary can spoof stuff. Without, for this analysis, we assume a synchronous type computation, network computation, rounds and so forth, but that's not necessary. And how are we gonna map computational power to number of parties so that we can talk about, the same thing? Is by we assume a flat version of the world in terms of computation. And here the analysis in the random oracle model. So this number of queries that parties are allowed to random oracle per round. Okay, so then we have, if you have T guys, this would be the total number of queries that the adversary can produce in one round. And then you can map it to the good guys, bad guys. Okay, that was the model. And as I mentioned, there is a beginning protocol block in the beginning called the Genesis block. And we'll get back to that later. Okay, and here's an example of how this would work. You have a blockchain like this, and this V has to be true for the transactions to be valid, according to the application. Okay, so it was basic Bitcoin backbone stuff. And what we did was we identified basic properties of this data structure. One called common prefix, we should encompass agreement, right? So everybody is decentralized, it has its own data structure, but if you look at the prefix of this data structure, right, it has to be the same. That's a common prefix. Chain quality captures the fact how much stuff parties can, can enter into the data into the blockchain, all right? And chain growth, meaning the parties keep trying, doing these proofs of work, and the data structure should grow. Okay, that captures like the liveness property. So we came up with these properties. And then we show that applications, once you show that these properties hold, except with negligible probability, you can derive properties of applications in a black box way from these other data structure properties. Okay? So what were those applications that look like? Consensus, which is what we're talking about now, and the ledger application, which is Bitcoin, or also called Nakamoto consensus. All right, so we didn't start this. Nakamoto himself started this in an email thread saying, you can use the proof of work chain as a solution to the Byzantine generals problem, and what he meant is Byzantine agreement problem. Everybody starts with an initial value, that's Byzantine agreement. And sketch this thing in the email thread. which I'll tell you basically says we want to hack a Wi-Fi network, so everybody has to start at the same time for the attack to be successful. Okay? Except that he said, well, they don't care when to start, right? The start time, but they have to be, they have to agree, but not the validity condition. So which means that doesn't solve the problem we are trying to solve. And in fact, this was the approach. So remember, now the input value to the transaction value would be the input value of the parties. So he suggested this. The end parties start mining and trying to insert their input value to the block. But if they see something, a longer blockchain, they switch. Okay, and they stick to the new value. Okay, so that means that with constant probability, the adversary wins. Okay, so he can find a proof of work first, install the value of the adversary, and then everybody's going to adopt it. Okay, so in some sense, this doesn't work. And this is reflected here. This is how these properties follow from the data structure properties. And this is saying it can only be satisfied if the computational power is negligible. All right? And an easy fix of this protocol gives us up to 1/3. Okay, and the fix is, okay, you get a longer blockchain, you adopt it, but you don't give up on your value. You're still trying to insert your value. Okay, and you do it long enough, then you shave, you prune the blockchain, you take majority, chart of bounds gives you both agreement and validity, but only up to 1/3. Okay, which is not optimal. And what we did was suboptimal because of chain quality. And we can actually do this by a more elaborate protocol where we use something called 2-for-1 proofs of work, okay, which is based on, you can think of these properties as slowing down, making everybody equal, okay, but imposing that property at the transaction level as well. Okay, for that you need to do 2 proofs of work. And then the question is, you're limited in this model by Q queries to a random oracle. Okay, what prevents the adversary from switching from the protocol layer to the application layer and so forth? And this thing, the 2-for-1 trick does it. And I'm not going to go into detail. All right, that's what I said. And this is saying we're doing both transaction layer and both at the protocol layer and the transaction layer. Okay, same type of thing, and that works. Okay, so we can get consensus in some sense, tolerating the optimal number of parties. All right, so this is where the signatures of work come into place, because remember, in the classical setting, we saw this double-strong approach where the parties would sign messages and distribute them around. So let's look at if we can have some sort of similar primitive like that. So it's a permissionless signature-like primitive, same goal as before, right? Slowing down, making egalitarian situation. And we want to reduce, same as in the classical sense, in the classical setting, the consensus to this new primitive. And here's a contrast with SOWs to classical signatures, which are transferable, same as classical signatures. And here you can, but in order to be able to sign conflicting messages, you have to invest twice the amount of work. Okay, and that already gives you a hint why this apparent contradiction is not an inconsistency. Okay, you could not play the scenario where the sender signs one value, one message for one guy, and at the same time a conflicting message to the other guy. Okay, in a nutshell, that's the reason. And there's funkier properties, such as here, there's no secret key. Okay, in this primitive, you still use to authenticate something, like I've been doing work on this argument, okay, but I use the resources I have are my own computational resources. And another property is here the exact, when this is verified is important, as opposed to classical signatures. All right, so in some sense, they have to be fresh. And we come up with the properties that have to be, that this primitive would have to satisfy. Correctness, a natural one. See, if you're in the classical setting, you sign something, you're going to be successful. Okay, here, not always. So you need to lower bound the probability that the signer succeeds. Instead of unforgeability, we have moderately unforgeability. Okay, which has to do with this moderately hard functions. They are subject to key tampering, where the tampering, there's no key, but the adversary can force stuff that you have to work on. Okay, so even in that case, they have to be secure. And most importantly, it has to be a runtime independence. There has to be satisfy a runtime independence property, meaning we need some sort of anti-concentration property so that not everybody is successful at the same time. Okay, otherwise, these protocols will get jammed. Okay, that's intuition. And also importantly, look at this T thing that is all over the place. That essentially means T steps. So we're going to be living in the exact security regime. Okay, no polynomial time, but fixed computational model. You have to take fixed T number of steps. All right, so this way we achieve a new protocol tolerating the optimal number of corruptions. This should be an number 2 over here. And kind of looks like this, and is implemented we implement that in the random oracle model. All right, so in some sense, you can think of the common approach in the classical setting and the blockchain setting in the sense that parties try to sign and broadcast their input, and then everybody runs the protocol, builds some data structure, and does something on data structure and produces the output. All right, how many minutes? 5? Okay, so how do we circumvent one of these impossibility results? Recall that we have this first block called the genesis block that the blockchain has to start from. Okay, and this in Bitcoin with this arguably unpredictable headline in the Times of London. Okay, so the mining had to start on that string. And that happened for everybody roughly at the same time. And that means, so we're going to see now is, remember the strategy setup that we had in the model, the genesis block, is actually not needed because you can start from scratch. Okay? And this is actually this approach of using proofs of work as an identity assignment tool was proposed by Aspnes et al., pre-Bitcoin, pre-blockchain stuff. Stefan, the problem with that was that they got something, but the PKI was not consistent, so they could not run classical protocols. And Stefan fixed that in Crypto 15. Okay? And the idea is that first you run some challenge exchange phase. You exchange a randomness, okay, and then you start mining and doing the computation. All right, and notice that the adversary can start way ahead of the honest parties. All right, and the reason for that this works is that you send randomness out, you get hashes of randomness coming back, and you check that your own randomness comes back. Okay, so that's the fresher indication of fresh stuff that you have. So regardless of what the adversary started doing this a long time ago. So this way we get this picture where, so here we have the classical world with all the bounds. Here's the blockchain world. And the layers are the communication primitives that we have, the type of setup that we have, and the type of assumptions, computational, information theoretic or computational. And here, when you see point-to-point communication, private setup, meaning PKI, private state setup, okay, using signatures, you get the Dolev-Strong result. And here you get the border-thing result where there was no setup. Okay? this blockchain abstraction using some sort of setup, what we call public state setup, can give us something similar 1/2, but this stuff that I just mentioned, give us 1/2. So this is the apparent contradiction between the green and the red bounds in the classical world. And remember we saw this, right? The basic reason is what I mentioned before, that now the adversary cannot do this. Okay? And how do we capture this? You all know what simulation-based security is. Okay, so we are trying to capture this in a more general way. If this was a communication channel functionality, right, where party PI sends party to PJ, in this framework that we call resource restricted framework, okay, so the party can do this. So this would be a wrapper. The party would try to send a message, and intuitively, the wrapper is going to check that some condition happened. This might be probabilistic and so forth. So only in that case, the message will be delivered. Again, this is an example of why the sender could not send two messages simultaneously. And here we can wrap other things. Okay, so again, I mentioned look at this T parameter all over the place. This is the exact security realization when you want to do things like this, as in prior works such as exact security of signatures, time release crypto, exact hardness, and more recently verifiable delay functions. All right, to summarize. So we explained this apparent inconsistency in bounds and number of corruptions and set of assumptions. We can do consensus tolerating minority of corruptions with no trusted setup. We're trying to explain things more formally and more globally, broadly, using this framework of resource restricted crypto. Also, we identify properties that this type of primitives have to have to work on the blockchain setting. And open problems is the construction we have is based on the random oracle. So you would like to have this in the standard model. And some initial step for a broader related primitive that we call iterated search problems are one step in that direction. We can instantiate this type of primitives based on standard properties of hash functions such as collision resistance and randomness extraction. If you're interested, so this is the consensus from Signature's paper. The resource restricted thing is we're working on it. This is the consensus from scratch. The beautiful picture is in this taxonomy paper that we wrote with Agilus. And this latest stuff, basing these primitives on in the standard model, is in the ePrint. Right, thanks.
Why do you have this, you have in your definition of signatures, maybe I'm missing something, but why this bounded, like the runtime independence of the honest parties? Isn't this like trivially achievable by just flipping coins and then, is there something I'm missing?
In the random oracle it's achievable easily. But if you want to do it,
Can't you add it to any primitive that you came up with the other four properties by just having, specifying that if you're honest, you flip coins? Or are you trying to get some sort of rational guarantees as well?
rational.
Like this against a stronger model?
No. So we can talk about this later. But you need this. It doesn't happen automatically, and especially if you want to do based on exponentiation or things like that, you don't get these properties. But it should be clear that if everybody gets lucky at the same time, the whole system gets jammed up, right? So you're trying to do this, there's no progress. It's hard to get that thing. And if nobody gets it also, there's no progress. So you need some sort of...